Homework 1, problem 12. The question here asks you to write the volume charge density using a delta function for a plane of charge at z equals 0, that's this red situation, a line of charge at x equals 0, y equals 0, that's this green line here along the z-axis, and a spherical shell with a total charge q. And so that's the blue situation you see there. Now, in order to do each one of these, I'm going to use the Dirac delta function. The Dirac delta function has a fun property, which is it lets us pick a value. And so very specifically, if I have a function, f of x, which has the following plot, then when I look at the expression integral dx f of x delta function of x minus a, what this does is it allows us to choose the value of f of x. This evaluates to f at a. So it allows us to choose the value of f of x at x equals a. And so it allows us to choose this value right there. We're going to use that to try and justify the fact that if I have an expression, so let's look at the plane charge first. Okay. If I have some volume, okay, and I look at the integral d3x over that volume, I should be able to write this integral dz, some area function, as a function of z. If I want to fix it to just z equals 0, I need to have a delta function of z minus 0, or just delta function of z, multiplying this area element. And so the justification that I'm going to give for that then is that I can make my rho as the surface charge density times the delta function at z equals 0. And that's going to give me the area there. I'm going to use the same justification for part B. And that is if I have an integral of d3x, and I want to write this as an integral of dx dy times some limit function L of z, and I want to pick that out for x and y. The actual multiplication that I'm going to need is my charge density rho is going to be lambda, and it needs to fix the x and the y coordinates. And so that's how I'm going to justify part 2. And this is all using simply that property there of the delta function that we want. So to do part C, I actually have to start integrating. Here, if I have an integral that does not cover the surface of my sphere, I'm going to get 0. All of the charge is on the surface of the sphere. And if I do cover the surface of the sphere, I get the total charge. And so that means I'm fixing the charge to the position of the sphere. That's going to suggest that my rho of r must be some constant k times a delta function of little r minus capital R. And this is going to fix the r value to the surface of the sphere. That's the justification we went through before. But I have to find what this constant k is in this case. And so to do that, I simply do my typical I find the definition of total charge in terms of the charge density. This is integral d3x of rho of r. In polar coordinates, without theta and phi condition, this d3x becomes integral from 0 to some big thing, whatever it needs to be, dr r squared. And then rho is going to be k times delta function of r minus capital R. But we know what this is. This is going to be 4 pi capital R squared k. And this is equal to q. Solving for k, this says that k is equal to q over 4 pi capital R squared. And so that says that my rho of r is going to be q over 4 pi capital R squared delta of little r minus big R.